So we can start talking about a review of general linear models. Yeah, I usually keep you the whole time. Just know that. I usually start 5 minutes late and then end on time. By the end of the semester, the front end starts to drag a little bit as people get more buried in things, but we're only 3 minutes late today. That was pretty good. So you've all had linear models already. I know that. And some of you may have had them from me as opposed to other people. But I want to make sure that you understand the way that I talk about things. So this should all be a review, but potentially from a different perspective or using different terminology or notation, because I approach everything pretty much the same way. So starting with what you know, hopefully will make the new stuff go down a little bit easier. So if you're sitting here thinking, I already know this, good. That's the point. Plus it's 3 o'clock on a Thursday. Has the snow started yet? Anyone?
Yes.
God.
Sorry.
No more snow. We can't take it. Oh, goodness. Thank goodness for grocery delivery, though. I'm telling you, it's worth it. Walmart and Hy-Vee will bring the groceries to you. You don't have to leave your houses or apartments. It's beautiful. All right, so we talked about this. What is the general linear model? This stuff. So what these variants all have in common is the assumption about the residuals. They're supposed to be conditionally normal. They're supposed to have constant variance because the normal distribution only has one variance, and they're supposed to be independent. We're leaving the independence one in place for a while, but we're changing all the other ones. So, more concretely, a one-slope example. Let's say that I'm predicting income in thousands of dollars, and I'm doing it with education. So education is on the x-axis here, and income is on the y-axis. The simplest possible regression model that you would ever have is called an empty model. Empty means no predictors. This is something that I do for pedagogical purposes when I teach regression. We are going to do it for pragmatic purposes in this class, because this first model, if I know nothing else about a person, what is my best guess for their outcome? The grand mean. Beta 0, my fixed intercept, is the mean. So knowing this means that I understand how my model is working, because I should be able to get the mean back from my output. And that sounds like you shouldn't have to do that, but in generalized models you do, because the way that the software estimates things in terms of how it's parameterized varies. For instance, in predicting binary outcomes, SAS defaults to predicting the probability of a 0. What? Who does that? And in ordinal models, some of the parameters predict the probability of a lower response and some of them predict the upper response. And starting with an empty model where you're just trying to recreate the mean or the proportion in each category helps you understand what your model is doing under the hood. So let's say that I want to predict this person who's at the relatively high end of the distribution in income and in education. They have a value of 17.3. In this sample, they made, no, that's not them. They are high. They're 58.8. But the mean for this variable is right here. That's the purple line. So that's my prediction for them, is an income of $17,300. That's way low. So their residual is positive. The variance of the e's across people I can compute like this. So you're used to seeing formulas that look like this. What they actually got minus what the model said they were supposed to have, which is my y hat here. At this point, what the model said they were supposed to have is the same for everybody, just the mean. So y minus the mean, square that, add it up over people, and divide by n minus 1, because we had to figure out the mean in order to figure out the variance, that thing. That's how you compute variance. That is the formula for variance. So this is our starting point in these models, is 190 is all the variability in income that there is to be had. That's the prediction if I use this purple line. Now let's put education in the model. Now I have two fixed effects. I have an intercept and I have a slope. So you will hear me call these fixed effects because they are constants. In further coursework, you will be introduced to something called random effects, which are variables instead. And I know that's coming, and that's why I start off by calling these fixed effects. But everybody gets the same beta 0 applied to their score, and everybody gets the same beta 1. Now note, what I've done to years of education here, I have subtracted 12. Why might I do that? Have you seen this before? Adding or subtracting a constant to a predictor before you put it in the model? Some people call it centering or grand mean centering, constant centering. Why might I do that?
In this case, because you're assuming everyone graduated high school.
I'm not assuming everyone did, but 12 is a high school reference, yes. So that's why I might have picked 12. Why would I subtract anything at all?
Because you want to be able to include negative values for your acting.
Getting warmer. Yes.
Is it because like high school is the minimum, like 12 years is the minimum, or are you only looking at like college?
In this sample, the minimum I think is like 3rd grade, and it goes up to doctorate. In years of education, this is an American sample. Here's your hint. This guy right here, that's why. What's an intercept?
It's what the income would be if our slope was 0.
Not the slope,
The x value.
the predictor. The definition of an intercept is the expected outcome when all the predictors in the model are 0. If I didn't subtract 12, this intercept would be the expected income for someone who never went to school. That's not wrong, but it sure is weird. And it's also not possible in the sample. So by moving the reference point for the model, centering, I have changed it. So now this beta 0 intercept is the expected income for a high school graduate. I've got one of those. So that's why the picture here, 0 equals 12 years on the legend. Now, that point right where my mouse is, that's your intercept. Beta 1 is the slope for how expected income changes per unit of my predictor, which is per year here. That's the blue line. So now if I look at the prediction for this really rich person relative to the rest of the sample, I'm closer, right? It's closer to where the dot is, but it's not that close. So now I have a predicted outcome of 28.4, and the residual is smaller than it was. And if this predictor is useful, everyone's residual should be a little bit smaller than what they were without predictors. So to put that another way, what I have done is explained, and I'm putting that in air quotes, by the way, part of the variability in income. The difference between the empty model purple naive line prediction and the education model prediction is this much. We call that explained. Why is it that this person makes more money than everybody else? Because they went to 20th grade. Yeah, it starts to break down at some point. I know you're all doing the math like, what grade am I in? But, right, that's why we're here in part. We'd like to make more money, and more education should help us make some more money, at least in theory, assuming you're not going to be a professional athlete or something instead, where you get lots more money for not any education. But now there's a whole lot we don't know. Because why is this person so much higher than everyone else who went to 20th grade? That's unexplained. So 162 is now how much variability there is in the residuals that's left over. And we can compute an R-square to describe the size of this relationship. This is the adjusted version. I'm computing it in a way that uses this rather than sums of squares for a more general case. What it was minus what it is over what it was. So 0.17 is the proportion of variance that is attributable or explained to education. I don't care which word you use, explained, accounted for, attributable, responsible for, any other synonyms I'm missing? Yeah. This is possible because we have this separately estimated variance in the first place. We won't have this after this unit in this semester. All right. Yeah. So more generally then, these linear model terms will continue to apply this entire semester. An intercept is the expected outcome when all the predictors are 0. If there's no predictors, it's just the mean. Each slope tells us the difference in y for a 1-unit difference. Note that I'm saying difference and not change. That's a semantic distinction to most people, but not to me. The reason that I don't say change is because people don't change into each other. They're different from each other. I reserve the word change for longitudinal research in which they are literally changing. Like I have changed from a 46-year-old to a 47-year-old on my birthday next year. My son will change from 8 to 9. But people who are higher than others are just different. So this is a cross-sectional interpretation. Each slope is going to have 6 relevant characteristics. An estimate and a standard error are the 2 you absolutely need to tell people about. The slope is the best guess, comes from making the data the tallest. The standard error is an index of how wiggly that slope estimate would be across samples. It's defined as the difference on average between the sample slope and the population slope it's supposed to be. We don't ever know what the population is, so I'm not going to worry about that. But more is worse. So it's an index of imprecision or inconsistency, standard error. These 2 things are all you need to compute everything else on this list. So then your test statistic as to whether your slope is significantly different than 0 or whatever null hypothesis you pick is treated as a t. If you're using denominator degrees of freedom, it's treated as a z if you're not. And then the p-value comes from either of those distributions. Probability of a result as extreme or more if the null hypothesis is true. So we will still have estimate standard errors and p's. We will likely not have denominator degrees of freedom, and that means this is going to be treated as a z instead. Confidence intervals is another thing you can compute if you want to. I personally hate them. I find them not helpful, but I'll show you how to get them out of the output in case reviewer 3 wants confidence intervals. If you give them the standard error and the estimate, though, and they know how big your sample is so they can compute t-critical, they can make whatever interval they want. So to me, that's less helpful to compute one of them than just to give them the information with which to compute anything. So notes about that. I call this process a univariate Wald test, estimate divided by standard error. Some people would yell at me and say that's only true if you're using z instead of t, but who cares? So we will see a mixture of t's and z's across software, but most of them will be z's this semester, and that's probably a good place to stop. So is this sounding familiar? Good, it should. We're easing into the semester. All right, 313. Questions or comments before we adjourn for the week? Yeah.
So when we did the centering, is that basically just to make the model better, or like why?
Centering predictors ensures at a minimum that your intercept is meaningful, but it also ensures that main effects of models that include interaction terms are also meaningful. The way that I think about it is the intercept of your model, let me go back to the picture here for a second. The intercept of the model is like the "you are here" sign on a map, right? If you go to an airport and you're trying to figure out how to get food, the first thing you need to find is the star, like "you are here," which way is the Chipotle? You know, which way is this? The intercept is the "you are here" sign. And it's not helpful if the "you are here" sign is on a completely different map in a different terminal. So it's like from there, when we talk about a 1-unit increase or decrease, like what is it relative to? Having the intercept in the middle of the data makes it a more useful point of reference to talk about my reference person has this expected value. Now this is what happens if I turn the knob and increase this predictor or decrease this predictor. Sure. There's more about that in the slide deck to come too, but I wanted to make a point that in my world, all predictors are going to have a meaningful 0, always. Anything else? Okay, thanks for coming. Hope to see you next week. Have good weekends. Let me know if you need anything. Good luck with the snow.
Thanks, Lisa.
Thank you.